Welcome to this discussions on the cross-section balancing. Um, the main course material has been delivered, and now for a few more discussions, questions I will be raising, and you can check whether you can answer these questions. I will be giving you hints also. In fact, most of these questions, in some way or other, I have already explained. So if I write the first question, did you find or did you understand the drawbacks of cross-section balancing? What are the limitations? What are the drawbacks of this process? You can look at my videos and try to find out the answer. In addition, I can add a few things. What about the starting cross-section? And its accuracy. Many times, the cross-sections are prepared almost accurately in the field based on field work, but there are cases where the geologist is bound to make some speculation in matching the story. In the published cross-sections, not always you will find which parts are the speculative and which parts are strongly found in strongly based on the field findings. So dealing with cross-section, picking up randomly from the published paper is not always safe. It can give problematic balance sections. The balancing may not go correct because the starting cross-section itself may be problematic or some speculations involved. When we are dealing with cross-sections, when we are dealing with the seismic images, when we are handling the seismic images, we first find out or decipher the structural geology, but this can give non-unique results. So what one interprets as a normal fault, some other person can interpret as a reverse fault. Since they are starkly different, the balance cross-section can also vary significantly. This non-uniqueness can be reduced if we are not only dealing with vertical cross-sections, but also horizontal cross-sections of seismic images. For example, what you find on a vertical cross-section as steeply dipping fault, say normal fault, and suppose you make an additional observation on the horizontal section that there are polygonal in appearance. These faults are polygonal in appearance. In that case, there is a high chance that these normal faults are non-tectonic or atectonic, and they can be produced due to differential compaction of the soft sediment which is present here. So dealing with a non-tectonic fault with the hope that we were dealing with a tectonic fault may have problematic results in terms of the cross-section balancing. The third drawback or problem in cross-section balancing is that sometimes geoscientists are unable to quantify the volume change or percentage volume change. And in that case, the balanced cross-section, even though you come back to horizontal, undisturbed, undeformed beds, some inherent problem might be there. So in these ways, the cross-section balancing is not free from error. It does not mean that we will not do cross-section balancing. It can mean that we have to find out the best possible way of doing cross-section balancing. If a problem is found, then we have to solve it to the maximum possible extent. I go to a second question. The question is, are all sedimentary layers horizontal before deformation? As per one of the Steno's laws, all the sedimentary layers before deformation are horizontal, but that is not the case. In fact, this question is more fundamental in geology and is basically a prerequisite to the, should be considered as a prerequisite study before doing the cross-section balancing. The answer is very simple. If the depositional surface is horizontal, we will expect horizontal layers to be deposited. But if the basement is undulating, then the deposition pattern will not be horizontal, will not even be parallel to the basement geometry. This curve is defining the top surface of the basement, and the sedimentary layers will not be deposited like this. This is not going to happen. So what is going to happen? Most commonly, where there is a depth, the sedimentary layer is thick, and where there is a less depth, the deposited layer will be shallow. So this is going to be the pattern. So in this case, the sedimentary layer is non-horizontal, and it is also of variable thickness. A note for the beginners, this sedimentary layer, though now looks curved, is not produced, this curvature is not due to any deformation. Even if we wish to call this sedimentary layer as a fold, we can at best call it a primary fold, or non-tectonic or atectonic fold, or a primary structure. And what we said in cross-section balancing, our aim is to look at the deformed units and balance the section and come back to original horizontal layer. In this particular case, the original situation was not about horizontal layer. So if this sedimentary layer gets deformed, complicated, folded, faulted, and then you try to balance, if we go back to this geometry, this is also not correct. This is not going to be a correct approach. Okay. Now I can go to the third question. Do we always balance tectonic structures in the cross-section balancing exercise? And again, if you look at, actually you can pause the video and look at my previous lectures recorded and try to see the answer. The answer is somewhere there. I hope you stop the video, and here is the answer. In case of salt dome or diapiers, or instead of salt, let's say mud domes or mud diapiers, geoscientists have tried cross-section balancing. Are salt domes tectonic features that the plates move and they compress or they extend the crust and therefore the doming is produced? The answer is no. What about mud domes? No, they are not necessarily produced by tectonic stresses. Once a salt dome is produced or a mud dome is produced, they can be further modified in geometry after the action of the tectonic stress. So these are the cases of atectonic. They have atectonic origin, and here also we try for cross-section balancing. Just to recollect quickly, consider two layers deposited, layer 1 and layer 2, with density rho 1 and rho 2, and the situation has been such that rho 2 is more than rho 1. That means a denser material has been deposited over a lighter material. Denser material's tendency will be to go down. The lighter material will try to move up. So the lighter material 1 moves up in this pattern, producing domal geometry. Now, if this material was salt, this is salt dome. If this material was what? Mud, then this can be called as the mud dome. So from here to there, the density difference was the key factor, not the tectonic stresses was the case. And in this case also, we apply cross-section balancing. So both for the tectonic structures and also structures which have atectonic or non-tectonic origin, we apply cross-section balancing. Here, layer 1 and layer 2 started from initial horizontal position. The salt domes are to be balanced so that we go back to this scenario. Let's go to the next question. Can you give an example of microstructure? A microstructure where the principle of cross-section balancing is applied for some purpose. Any example where, in case of a microstructure, the principle of cross-section balancing is applied? Again, the answer will be found in my previous lectures. You should stop the video and go back to the old lectures and find out, and then come back and check the answer. Certainly for microbudins, we can find out, we can apply principle of cross-section balancing, especially the area balancing. But then what is our purpose? When we apply area balancing method on the microbudins, we find out strain parameters. Starting with elongation, then percentage elongation, then shortening, then quadratic not shortening, sorry, this is out. Quadratic elongation, reciprocal quadratic elongation, and the logarithmic strain or the natural strain or the fundamental strain. All of them can be obtained, and this have been discussed. Note that by applying the area balancing principle from microstructures such as microbudins, we can find out the strain parameters so that we can have an idea about the rocks, how much is the strain that the rock has underwent in the past. When we apply area balancing on cross sections deduced from field studies, that information is useful in a different way. Strain analysis can be the secondary work associated with the cross-section balancing, but is not the primary aim. The primary aim is to understand, are we able to do proper cross-section balancing, come back to horizontal layers, undeformed layers with no gaps, no overlaps. If it is so, then we have understood the deformation process. This is undeformed and it's a deformed product. If we have understood it completely, that means the details of structures can be fit in a tectonic context. When we are dealing with microstructures and applying area balancing, this is not the case. Area balancing on the microstructure such as microbuddins can at best give us the strain parameters such as these things, such as these parameters. If we make serial thin section, sectioning, and we have an idea about the volume of rock, we are thinking in terms of 3 dimension, then we may be able to apply volume balance principle on the microbuddins. It is important to note that not just the microbuddins, but buddins in mesoscale can also be attempted to find out the different strain parameters based on area balancing. So with this, I can finish this short lecture right now, and 1 or 2 more presentations will come on cross-section balancing, where I'm going to bring new issues and we'll go one step ahead from what has been taught already. Thank you.